Question 1. This question is to determine the concentration of the dissolved oxygen in the samples of river water. And it follows the few steps below. Okay, the first step, use a 550 cm3 graduated syringe, which label A, B, C, D, E, to collect 5 separate 30 cm3 samples of this river water. And after that, in the lab, carefully add 5 cm3 of 0.22 mol per dm3 manganese 2 sulfate into the syringe. Let's say now start with this syringe A and mix well. Okay, after that, add 5 cm3 of alkaline aqueous potassium iodide into the syringe A and mix well. So this one we need to know the volume. Okay, it start with 30. After that plus 5. Now plus 5. Total is 40 until the step 3. And during this step, something will happen. The manganese 2 will react with hydroxide, and it will form manganese hydroxide. Okay, after that, it will react with the oxygens and being oxidized to form this compound. So after that, next step. Step 4 is add 10 cm3 of the dilute H2SO4 into the syringe A and mix well. So the compound that produced just now further reacts with the iodide, and iodide from this step 3, potassium iodide, and eventually it will form the manganese 2 and iodines and H2O. So in this step, of course, we will see the iodines formation, means the brown solutions form. So means the whole mixture will turn brown because the iodines are produced. Okay, after that, step 5. Transfer the contents of the syringe A into 150 cm3 conical flask. Rinse the syringe A using 10 cm3 of distilled water and add the washing to the conical flask. Okay, so now the total volume of the reaction mixture is 30 cm3 plus 5 plus 5 plus 10. So it's total 50 cm3 in the syringe. Then this 50 cm3 mixture introduced to the conical flask plus 10 cm3 of the washing. This step is just to make sure all the reaction mixture get into the conical flask. Okay, after that, last step, carry out one accurate titration of all the contents in the conical flask with 0.002 mol per dm3 aqueous sodium thiosulfate using a starch indicator. So for this one, before the titration, we need to use the starch indicator because the starch will react with the iodines produced and it will turn blue-black. So during the titration, the thiosulfate will react with the iodines and the iodines will reduce to iodide. So means at the end point, the blue-blacks will disappear because the iodines eventually will finish. Okay, so these are the steps involved. And part A, aqueous sodium thiosulfate can be prepared from this salt, thiosulfate, this pentahydrate. So this sodium thiosulfate pentahydrate, we need to use the molar mass for the calculation. Part 1 determines the mass of this salt required to prepare 500 cm3 of 0.00200 mol per dm3 sodium thiosulfate solution. Okay, so because it's asking mass, so of course we know that is N equal to the mass over molar mass. So means in order to get the mass, we need to get the mole and the molar mass first. So the mole we can get from the solution, the volume and its concentration. It's just mv over 1000. So 0.002 times 500 over this 1000. So we get this mole. This is the mole of this sodium thiosulfate that need to produce or need to form from this salt. Okay, molar mass is 248.2. So we just use the molar mass times the moles that calculated just now. We'll get the mass. The mass that needed to prepare the solution means 500 cm cube of 0.002 mole per dm cube. Sodium thiosulfate solution, we need 0.2482 gram. Okay, so next part. Identify the piece of apparatus that should be used to prepare 500 cm cube of 0.002 00 mole per dm cube sodium thiosulfate. So this one is you need to specifically mention what is the apparatus. Normally when we prepare a solution, we will use the volumetric flask, something like this. So and of course you need to mention the volume as well, right? So 500 cm cube volumetric flask. Try not to mention conical flask. Conical flask normally we use for titration. Try not to use measuring cylinder, right? Because it needs to be a very accurate this titration, and the concentration of the sodium thiosulfate is very important, right? So volumetric flask is the one that we must use. After that, part B. The graduations on the 8th syringe are every 1 cm cube. So this is a very important hint. Already told you each of the graduations will be 1 cm cube, something like this. Let's say from this 10 to 20 cm cube. So each graduation is 1 cm cube. So means 11, 12, 13. If let's say now we want to get the uncertainty of this syringe, so we must get from this half graduation. So because each of the line it will be 1 cm cube different, so means between the lines will be 0.5. So the uncertainty for this syringe will be plus minus 0.5. That's how we get these uncertainties. Okay, now part 1. If we know the uncertainties from the graduation given, so and we get this 0.5 means plus minus 0.5 here, so we can do the calculations. Part 1. Calculate the percentage error in the measurement of 5 cm cube of alkaline aqueous potassium iodide. Okay, so first we need to know how many measurement we need to take. So if we follow the procedure, because the solution added one by one to the syringe, so when this 5 cm cube of the alkaline aqueous potassium iodide introduce or get into the syringe, we need to read 2 times actually. Okay, so therefore in this part we need to use 2 times of 0.5 over the volumes of the solution times 100%. So we get 20% for this percentage error. Okay, part 2. Place 1 tape in each row in table 1.1 to show the effect, if any, of using larger volume of alkaline aqueous potassium iodide. So first, uncertainties of the measurement. So this one has no effect at all, because if we use the same syringe A, the uncertainty is still the same, because the graduation never changed, right? So it has no effects. It's still 0.5 plus minus 0.5 cm3. For the percentage error, because use larger volume, let's get back to this. Percentage error is equal to this. If let's say now the volume used is larger, means the error is actually smaller, right? So therefore, we have this smaller effects. Okay, part C. The sample in the conical flask and the prepared solution of sodium thiosulfate are provided. Describe the following procedure for the experiment using syringe A. Okay, part 1. Prepare the clean burette before taking any readings. So this one is a very simple procedure, but many candidates actually not really able to give the specific procedure. Okay, so first, in order to prepare the clean burette, it need to be rinsed. Of course, you can start with the distilled water. In fact, many candidates also put distilled water first, but it must be followed by the solution itself. Rinse the 50 cm3 burette with the solution. 0.00200 mole per dm3 sodium thiosulfate. Okay, before filling with the aqueous solution, means before we fill up this sodium thiosulfate, we just rinse the burette with a small amount of the solution. Right, first step. After that, after it's being rinsed, then we will fill out the burette with the solution, and you need to mention this one. Is to run out some of the solutions through the jet or the tips by opening the tap. Again, fill up the sodium thiosulfate solution in the burette, okay, and run some solution out through the jet or the tips. How is it? Why we need to do that? After we fill up the solution, we need to open the tap, and we need to fill up this part, because there will be air bubbles in this part. By fully open this, okay, the solution will fill up this, and eventually it will prevent the errors later. So this is the 2 steps to prepare the clean burette before the titration. Okay, part 2. Carrying out the 1 accurate titration in step 6. Okay, this one, in the step 6, let's see. So this titration is again using the starch indicator. You need to mention the color change. Right, so again, we use the sodium thiosulfate solution titrate with the contents in the conical flask. So means we need to use this thiosulfate, react with the iodine with the starch. Okay, so to do the 1 accurate titration, so we need to add the sodium thiosulfate into the conical flask like this. Sodium thiosulfate into the conical flask. Of course, is the mixture with the starch, right? It's a blue-black color, and add drop-wise towards the end. Means when it's almost the end point, you need to add drop-wise, drop by drop, until the blue-black color disappear. Because we are using the starch with the iodines will form blue-black. So when blue-black disappear, means it's the end point. Okay, part D. Suggest why the reaction mixture is mixed well in the step 2 to 4. This is very easy. To mix well before the titration, we need to make sure the reaction is complete. Okay, part E. Draw a table for recording the titration result for the 5 sample A to E. You just need to construct the normal titration table. Right, so the 3 items must be there. Initial burette readings, final urea readings must put the units cm cube and the volume of the sodium thiosulfate solution used. Okay, these three items must be there together with this titration A, B, C, D, E, these 5 samples. Okay, part F. The overall reaction take place follow this equation. Oxygen react with the thiosulfate under acidic condition will form the products. So means later the calculation we need to use the mole ratio here. So let's start. A student carry out the experiment and determines the mean titer to be 12.65 cm cube. Calculate the concentration of the dissolved oxygen in the river water. Because it's asked the dissolved oxygen means this one, so we need to get the mole of the thiosulfate first. Then we can get the moles of oxygen because oxygen is 4 times lesser than the thiosulfate. So the mole of thiosulfate, so we just use MV over 1000, so it's a 0.002 times the volumes given, 12.65 over 1000, we get the moles of thiosulfate. So use this one, divide by 4, it will be the moles of oxygen because it's follow this equation, 1:4 ratio. So the moles of oxygen now is 6.325 times 10 power negative 6. Okay, this is just mole because it's asked the concentration in mole per dm cube. So means the mole now need to divide by the volume in dm cube because it's asking dissolved oxygen, means the dissolved oxygen in the sample. Sample that used is 30 cm cube, not including the reagent, right? So you just need to use 30 over 1000. So eventually you get this concentration, 2.108 times 10 power negative 4. Okay, part G. Freshly distilled water does not contain any dissolved oxygen. A student decides to run procedure on the samples of the distilled water, and at the end, it obtains a value of 2.26 times 10 power negative 5 mole per dm cube dissolved oxygen. Means instead of using river water, now the student use distilled water. Distilled water together with all the reagents that involve, like the potassium iodide, acid, and so on. Okay, part 1. Suggest why the student did not get a value of 0 mole per dm cube. Assume the procedure was carried out correctly. Okay, this one is you need to, of course, consider the others reagent. Because the water itself, distilled water, it might not have any dissolved oxygen, but the others reagents like the potassium iodide, acid, and even the starch also. So all these reagents, they might have some dissolved oxygen. So that's why during the titration, it's not totally 0 mole per dm cube, DO, dissolved oxygen. So this small amount of dissolved oxygen, it might came from the reagents. So that's the explanation. And part 2, suggest how the value of this 2.26 times 10 power negative 5 mole per dm cube could be used to improve the answer in part F. Part F, we get this concentration. So this concentration is actually the DO in the river water and the DO from the reagent. So it's a total amount. So now we use this one minus the moles here, the concentration here, because this concentration is from the reagents. So we just subtract this value from the final results in the part F. So eventually we'll get the actual dissolved oxygens in the river water. That's the improvement. So part H, suggest why this method is unsuitable for the sample of tap water that have been purified by chlorination, and there will be some chlorines there. This is very easy. Chlorine, we know that is more reactive or more negative than this iodine, right? So chlorine will oxidize the iodide to form the iodine, right? So and chlorine itself will form chloride. So it will be a displacement reaction. So therefore, this is answer. Chlorine will react with iodide, or you can say chlorine will oxidize the iodides to iodine, right? So that's why it's not really suitable to use this method for the tap water, right? Because the tap water, the chlorine itself will react with the reagent, not the oxygen. So it will affect the results. Okay, that's all. Thank you.